Hello and welcome. I am Dr. Pauline Fu. In this video, I will present hypothesis test for population proportion. Learning objectives. Explain the logic of hypothesis testing and test population proportion. And then we are going to use binomial probability distribution to do the hypothesis test about population proportion. Let's look at an example. A researcher obtains a random sample of 1,000 people and found that 534 are in favor of banning cell phone use while driving. So p-hat equal to 534 over 1,000. P-hat represents sample proportion. Does this suggest that more than 50% of people favor the policy? Or is it possible that the true proportion of registered voters who favor the policy is some proportion less than 0.5, and we just happened to use a survey a majority in favor of the policy? In other words, would it be unusual to obtain a sample proportion of 0.534 or higher from a population whose proportion is 0.5? What is convincing or statistically significant evidence? Okay. So in this example, you get a sample data. Sample size 1,000. Out of these 1,000 people, you found 534 in favor of banning cell phone use while driving. The question is this statistically significant for population based on the sample data? So when we observe results are unlikely under assumption that the null hypothesis is true, we say the result is statistically significant. Okay. So when something is statistically significant, it is unlikely to happen. When results are found to be statistically significant, we reject the null hypothesis. When we reject the null hypothesis, we are in favor of H1, a tentative hypothesis. Because H0 and H1, you must choose one. Our question is, if the sample proportion 0.534 is statistically significant, that is our question. Okay, to answer our question, we need to build a probability model. Okay, and first we need to check the condition. We need to say if n sample size times p, population proportion greater or equal to 10, we need to do this. This one is satisfied. So n is 1,000 sample size, p, population proportion. Because in population proportion, you're either in favor this policy or you do not in favor. So population proportion equal to 1/2, 0.5. So the sample size is sufficiently smaller than the population size. We can use a normal model, okay, to describe the variability in population proportion P. This P is population proportion P. The mean of the distribution P hat Okay, actually this is a p hat. Let me clarify. Okay. P hat is the sample proportion. Okay, the mean of the sample proportion p hat is 0.5. Okay, the mean of sample proportion equal to population proportion, and the standard deviation equal to population standard deviation p times 1 minus p over sample size, central limit theorem. Okay, central limit theorem. This is a graphical representation of sampling distribution of sample proportion. Okay. We know population proportion is 0.5. Okay, and our sample proportion 0.516. Not 0.16. This is our sample proportion 0.534. Maybe somewhere here. 0.534. And this number 0.516, it is just one standard deviation away. If you use 0.5 plus 0.016, and you get 0.516, this number here. And then if you use 0.5 minus 0.016, and you get this 0.484. Okay. Our result is here. Our test proportion P, sample proportion is here, 0.534. The question is this point statistically significant? Okay, that is the question. We may consider the sample evidence to be statistically significant if the sample proportion is too many standard deviation above the assumed population proportion 0.5. So go back to this diagram. So if we believe this point is far away from this point 0.5, we say it is statistically significant. And if this point is not far away from 0.5, we say it is not statistically significant. But how do you measure how far is far away? Okay, we need to do the calculation. Okay. So this is the formula to do the calculation. We need to calculate the Z value. By definition, Z equal to sample proportion P hat. In our example, it is 0.534 minus population proportion divided by population standard deviation is this number here. Okay, and our Z value 2.15. So this Z value, this is a 2.15 standard deviation above the hypothesis proportion. So therefore, use our criteria, we would reject the null hypothesis. What is our criteria? We say if it is beyond the 2 standard deviation, we consider it is significant. See here, 2 standard deviation. Okay. And our calculation result is more than 2. That's why we reject the null hypothesis. Okay. So this one said, why does it make sense to reject the null hypothesis if the sample proportion is more than 2? Why is this? Okay. Because the area under the standard normal curve to the right of Z equal to 2. This is normal curve, this is Z equal to 2. Okay, and if you have Z equal to 2, what is this area? what is this area, you need to find out. Okay, maybe you can use the normal table. Okay, normal distribution table. Given the Z value, what is this area? Okay, the result is 0.0228. Okay, so this is smaller than 0.05. That's why it makes sense to reject the null hypothesis if the sample proportion is more than 2. Okay. And this diagram shows that if we have a point here, this point is our 0.532. Okay, this point. Once you have a 0.532, you have a point. Can you find the area to the right of this point? Yes, you can find the area. Where? Go to the normal distribution table. Okay, find the Z value. Remember, find the Z value. Okay, Z value. And then this part, you locate 0.5. And then 0.03 is here. And the intersection part, okay, is the area. Is the area 2.28%. Okay. So that means only 2.28% of the sample proportions will be more than 0.532. That is another way to say that why we reject H0, because only 2.28% more than 0.532. Now we introduce classical approach to hypothesis test. If the sample proportion is too many standard deviations from the proportion stated in the null hypothesis, we reject null hypothesis. Okay, that is the classical approach. Usually this standard deviation we use 2. If it is greater than 2 standard deviation, we reject null hypothesis. Now we introduce a very important concept, p-value. P-value is the probability of observing a sample statistic as extreme or more extreme than one observed under the assumption that the statement in the null hypothesis is true. It looks complicated about p-value, but actually remember this. P-value is the area corresponding to sample statistic. In our example here, our sample statistic is 0.532. Okay, 0.5. Sample statistic actually it is here, 2.15. Okay. You get 2.15, Z value, 2.15. How do we get 2.15? We did the calculation based on central limit theory. We calculated the Z value. And this Z value is actually test statistic for the sample, 2.15. And once we have this 2.15, this point, go to the normal distribution table, you can locate this area. Okay, and if the test is a 2-tailed test, this area times 2, that is p-value. If the test is one-tailed test, the area is the p-value. Okay, so p-value is the area corresponding to test statistic. Given a test statistic like 2.15, given a Z value, you can find an area to the left of this Z value. Where? Go to the normal distribution table. Okay. So this diagram shows you all the value here represent p hat, means sample proportion. Our sample proportion is 0.534. Okay, and what is the chance of greater than 0.354? It is referred to this area. And this area, that is actually p-value. If you have one-tailed test, if you have two-tailed test, multiply by 2. So recall we get this z-value 2.15. Okay, so p hat greater than 0.534. It is the same as z-value greater than 2.15. Okay, this probability, they both refer to this area to the right. And this probability, you get 0.0158. Okay. So this is the p-value. So again, when the test is one-tailed, this is p-value 0.058. When the test is two-tailed, you have to use this number multiplied by 2, and the result is p-value. All right, let's review definition of p hat. P hat is x over n. X is the number of individuals having some characteristics. N is the sample size, and p hat is sample proportion. And also this is review of sampling distribution of p hat is approximately normal with mu p hat equal to p. Standard deviation of p hat equal to this one, central limit theory. And provided that the following requirements are satisfied, sample is simple random sample. Sample size n times population proportion p times bracket 1 minus population proportion greater or equal to 10. Sample values are independent of each other. So steps for hypothesis test for population proportion. Step 1, state the null hypothesis H0 and alternative hypothesis H1. There are 3 situations. If it is two-tailed, you have H0 is population proportion P equal to sample proportion P0. And H1 P not equal to P0. If it is left-tailed, you watch the H1. H1 is smaller than means it is H left-tailed. Right-tailed means H1 greater than. In 3 situations, you always have H0 is the same, see? Equal. It is just H1 different. When H1 different, it is determines the two-tailed test or left-tailed test or right-tailed test. And P0 is the assumed value for population proportion. P0 is not sample proportion. Sample is p hat. Step 2, we select level of significant alpha. The popular alpha is 0.05. If the question does not give you the alpha, assume alpha 0.05. Other popular choices, alpha 0.01 or alpha 0.1. And then compute the test statistic. Test statistic, it is just a formula, mathematical formula. So test statistic, sometimes we just say Z, ignore the 0. We just say test statistic Z equal to p hat represent population sample proportion. Remember p hat equal to x over n. And p0 is the hypothesized population proportion. N is the sample size. Using a classical approach, we need to identify critical region. Okay, what is the critical region? If you are given alpha, then you can calculate the z-value corresponding to half alpha. So for example, if alpha is 0.05, and you know half alpha is 0.05 divided by 2, so 0.025. And the meaning of half alpha means it is this area 0.025. When you have an area 0.025, we said this point is the z-value corresponding to half alpha. So z half alpha is a point, half alpha is an area. So the color in blue, it is just one point. This point represents z subscript half alpha. Okay. And this area in red color is area. The area is half alpha. And we call this z half alpha and negative z half alpha critical value. Okay, this critical value decide critical region. Critical region has another name, rejection region. Anything in the critical region has another name, rejection region. Anything inside the critical region or rejection region, we reject H0. Okay. So the critical value decide the critical region. Critical region is the same as the rejection region. Anything inside rejection region, we reject H0. For example, if this z half alpha is 1.96, suppose this z half alpha 1.96, okay, and if you have z value equal to 2.1, so obviously 2.1 is here, maybe this point, and this point is in rejection region or critical region, so you reject H0 when you have test statistic 2.1. On another hand, if you have test statistic 1.5, 1.5 must be smaller than 1.96. So your test statistic is here. It is not in the rejection region, so you do not reject H0. And this is a left-tailed situation. Okay, when you have left-tail situation, if the test statistic is here, you reject H0. When your test statistic is here, 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 you do not reject H0. So this gives you the criteria. How do you know you reject H0 or you fail to reject H0? Look at if test statistic is in the rejection region. If test statistic is in the rejection region, you reject H0. If not, you do not reject. Okay. And this is the right-tailed situation. If your test statistic is here or here or here, you reject H0. If your test statistic is here, 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 you do not reject H0. So how do we write down the rejection region? Okay, so when you have a two-tailed test, okay, if the test z subscript 0 represent test statistic, if test statistic smaller than negative z half alpha or test statistic greater than positive z half alpha, you reject the null hypothesis. Use the graph. If this is negative z half alpha, this point, and this point is positive z half alpha. If your z0 is smaller than this one, is here, is smaller than or greater than z half alpha, here is greater than, you reject null hypothesis. Okay, similarly, when you have left tail test, if your test statistic z0 smaller than negative z half alpha, you reject. So the graph is, this point is a negative z subscript alpha. If your test statistic is smaller than this one, means you are here. Smaller than this one, you reject. Last one, right-tailed test, and this is z alpha. And if your test statistic z0 subscript 0 greater than this one, means greater is here, you reject H0. Remember, you reject H0, not H1. Okay? When you reject H0, you automatically accept H1. The p-value approach, again, you need to calculate test statistic first. Okay, Z0. Once you have this Z0, go to, okay, suppose this is your test statistic. This area is the p-value if it is a left tail test or right tail test, okay? And if it is a left tail test and you get Z0 is here, this area is p-value. And if it is two-tailed test, and you have this is Z0, this must be negative Z0. Remember what is Z0? It is test statistic. What is test statistic? It is a result of formula. See, this formula, the result of this formula is test statistic. If you have two-tail test, the p-value is left area plus right tail area. Because symmetric, left tail area equal to right tail area, that's why you times 2. Okay, you get p-value. See, you sum the area when you have a two-tailed test. Okay, and when you have a left tail, the p-value is just this area. That is the p-value. P-value. And when you have right tail, this is the p-value. And this is Z0. Okay. And the decision rule, if p-value smaller than alpha, reject null hypothesis. This is true for all hypothesis tests, regardless it is one population, two population, regardless it is Z test, T test, F test, chi-square test. So it is true for all hypothesis tests. Okay, when p-value smaller than alpha, reject null hypothesis. Remember what is alpha? Level of significance. The popular choice of alpha, 0.05 or 0.01 or 0.1. Okay, alpha actually could be any number, okay, very small number, but those are 3 popular choices. And the last step, you state the conclusion. So now let's take a look at this example. In 1997, 46% of Americans said they didn't trust the media when it comes to reporting the news fully, accurately, and fairly. In 2007, poll of 1,010 adults nationwide, 525 stated that they didn't trust the media. At alpha 0.05 level of significance, is there evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased? has increased since 1997. Okay, the keyword increase means when you do alternative, when you write down H1, you should use a greater sign. That is the keyword increase. Okay. So again, this question, you are given the sample data. Sample size N equal to 1010 and X equal to 525. Okay, those are sample data. Based on X, based on N, you can calculate sample proportion p hat X over N. Okay, and then you, based on the formula, get test statistic. After that, you can use a classical approach or p-value approach, 5 steps. Okay, this is a very typical example of a hypothesis test for population proportion. Make sure you fully understand this question. Before we do any hypothesis test, we want to make sure the requirements are met. Remember 3 requirements. The first one, simple random sample. We usually assume it is simple random sample. The second one, sample size N times P0 times 1 minus P0. Okay, and P0 is 0.46. 0.46 here. This is P0, 46%. This is hypothesized population proportion, okay? 46% is here. This is P0, 46%. And this number greater than 10, so that means it is satisfied the second condition, okay? Since the sample size is less than 5% of the population, the assumption of dependence is met. Okay. So we check the requirements. Now we do the 5 steps. Step 1, set up the null hypothesis, H0. H0 said population proportion is 0.46. H1 said increased means greater than 0.46. And step 2, significant level, alpha 0.05. And step 3, calculate the test statistic. To calculate test statistic, you need sample proportion p hat. P hat equal to X bar. This is X over N. Okay. P hat equal to X over N. You get 0.52. And then you plug in the formula for Z test statistic. It is a p hat minus p. Okay, so the formula is p hat sample proportion minus p population proportion divide square root of p times 1 minus p over sample size. That is test statistic. Okay, sample size N. And you get test statistic 3.83. Okay. And once you get this 3.63, you can use classical approach. Classical approach means you need to identify the critical value. The critical value at 0.05 level of significance. Okay. Remember, because this is a one-tailed test, it is actually right-tailed test. When you have right-tailed test, this is alpha, this area is alpha, and alpha is given 0.05. Okay. When you have this area 0.05, go to the normal distribution table. This point must be 1.645. Okay, this point must be 1.645. And this point we call critical value. Critical value. And remember, critical value decide the rejection region. Okay, rejection region. So this one is rejection region. Okay, and now where is your test statistic? You get 3.83, maybe here. If this is 1.645, this is 3.83. Obviously, the test statistic is in the rejection region. So you reject H0 based on classical approach. You reject H0, okay? Because test statistic greater than critical value, you reject the null hypothesis, okay? So this is a classical approach. When you use the p-value approach, you need to calculate what is the p-value, okay? And remember, p-value is the area corresponding to test statistic. If you have a test statistic 3.83, this is the z-value. When you have a z-value, what is the area to the right of this z-value? This area represents p-value. And you can find this p-value, go to the normal distribution table. Okay, remember the normal distribution table tell you, given a z-value, you can find area to the right of the z-value or left, okay? And so we found the result is this p-value almost zero, okay? This area almost zero, okay? Remember when you get the p-value compare p-value with alpha. When p-value smaller than alpha, reject H0. This is universal truth, okay? Reject H0. So in our situation, we get p-value almost zero and alpha 0.05. So we conclude reject H0 based on p-value method. Okay. So this is the conclusion. I already conclude. So what does it mean reject H0? So go back to our H0. So we reject H0 in favor of H1. Okay, so we conclude the proportion increased. Okay, the proportion is greater than 0.46. So that is this example. Okay. So this is another example, okay? This is another example. In 2006, 10.5% of all live births in United States were to mothers under 20 years of age. A sociologist claims that birth to mothers under 20 years of age is decreasing. She conducts a simple random sample of 34 births and found that 3 of them were to mothers under 20 years old. Test the sociologist claim at 0.01 level of significance. So let's analyze this question. So this number is the population proportion, P. Okay. And this 34 sample size N, X is 3. Okay, so we can calculate sample proportion P hat X over N, so 3 over 34. Okay, those are the given data. And then based on P hat, we can calculate test statistic. Okay, so exactly the similar steps as we did in the previous example. So step 1, we need to determine the null and alternative hypothesis. So the null hypothesis, do we have answer? Yeah, okay, maybe from here. The null hypothesis is population proportion equal to 10.5% versus population proportion smaller than 10.5%. Why smaller? Because the keyword the simple random sample. We have keyword decrease. See, this keyword decreasing. If you have keyword decreasing, H1 smaller, H1 smaller, okay? So we have H1 and H0, and then we need to check the requirements, okay, to see if n times p times 1 minus p. There are 34 mothers sampled, so this one smaller than 10. So the sampling distribution of p hat is not normally distributed. Is not normally distributed. Okay, so what do we do? If it is not normally distributed, we need to use this method here. Okay, let X represent the number of live births to mothers under 20 years of age. We have X equal to 3, N equal to 34, P hat, sample proportion is 0.088. We want to determine whether this result is unusual if population mean is 0.105. Why this number is given 10.5%, remember? Okay, 10.5%, this number is given. 10.5% is the same as 0.105, okay? So we need to calculate the p-value. P-value is the probability of X smaller equal to 3. Assume population is 10.5%. Okay, so X is a random discrete number. So X represents number of births. It could be 0, could be 1, could be 2, could be 3. Okay, that is the probability of X smaller equal to 3. And we calculated this one is actually using the binomial. See, we're using the binomial probability distribution. And we get this p-value 0.51. And compare this p-value with alpha. Alpha is 0.01. Obviously, this p-value greater than alpha. When p-value greater than alpha, do not reject H0. Okay, do not reject H0. When p-value smaller than alpha or greater than alpha, when p-value greater than alpha, do not reject H0. So go back to H0. Do not reject means H0 is correct. H1 is wrong. So final conclusion, the population proportion is 10.5%. That percentage is correct at 0.01 level of significance. Okay. In summary, what I did in this video, I introduced hypothesis test for population proportion. There are two situations. One, if the population, the sample distribution p hat is normally distributed, we calculated the Z value, and then we can use classical approach or p-value approach. The second situation, as we just did the example, if the distribution of a sample proportion is not normally distributed, we need to use binomial distribution to simulate, okay, to calculate the p-value, and then compare p-value with alpha. If p-value smaller than alpha, reject H0. If p-value greater than alpha, do not reject H0, okay? That's all for this lecture. Thank you so much. Hope you learned something. See you next time.